are going to take chemistry test. This is pre-test. Use this diagram to answer the following 7 questions. There are 7 carbon atoms in the parent chain. It is called 1, 2, 3, 4, 5. That is 5 pentane. Numbering of this molecule will begin at alpha. Use this information along with the previous diagram to answer the following 5 questions. There are branches at carbon X, Y and Z. The branches at carbon X is called. There are 2 branches. One is containing 1 carbon and here is cyclopropyl. So methyl and cyclopropyl. There is a type of branch that is common between carbon X and Z. What is it called? This is the single line, that is methyl. Which carbon is able to make another bond? Y carbon present at Y has 3 bonds and it can make one more bond. So it is answer is Y. What is the IUPAC name of this molecule? Here first carbon, second at second place. There are 2 groups are attached, and at third place again there is a 1 group, and at fourth place is, and there are total 5. So pentane. The addition of a methyl group onto carbon dash would cause a change only to the name of the parent chain. That is why. Which of the following molecules is not an organic molecule? That is hydrocyanide. How many valence electrons are present in butane? Butane has 4 carbons, so 1 carbon has 4 valence electrons, so 4 carbons have total 16 valence electrons. Then C4 and 12 hydrogens are present in butane. 1 hydrogen has 1 valence electron, so total 12. 4 into 4 16 plus 12, that is 28. Which element has the same number of electrons? I have no proper idea, maybe zinc. Which of the following functional group is most likely to emit a pleasant sweet smell? That is ester or COOR. Can your answer to the previous question participate in hydrogen bonding? Why or why not? Yes, it has valence electrons. Which molecule will have the highest boiling point? Maybe that is the ester. How many hydrogen atoms does an alkene with n carbon atoms have? And in alkene, 2 carbon atoms are joined with double covalent bonds. So they have 4 hydrogen atoms. 2 carbons are joined by 4 hydrogens. C2H4. That is 2N. Next. Use this information to answer the following 5 questions. Molecule name, boiling point. Ethanol has this 78.4 degrees Celsius. 1-heptene has 94 degrees Celsius. Ethanoic acid has 117.9 degrees Celsius. Decane has 174.1 degrees Celsius. Which molecules have London dispersion forces? I have no idea about this, but maybe it is ethanol. Assume each substance is a liquid at room temperature. Which of these molecules can mix with water? Ethanol only, ethanol and ethanoic acid. 1-heptene only, 1-heptene and decane. Assume each substance is liquid at room temperature. Ethanol and ethanoic acid. Why they can mix with water? Maybe they have free electrons. Despite that decane does not have a permanent dipole, Its boiling point is much higher than ethanoic acid. Why? Decane can participate in dipole-dipole interactions. All other molecules contain oxygen. Oxygen decreases boiling point. Decane is unstable as a straight chain and likely it forms a fused ring structure. Decane contains the most carbon atoms. Maybe decane contains the most carbon atoms. Where would you expect methanol to place in this list? Before ethanol, above ethanol. Use this diagram to answer the following 4 questions. The addition of a methyl group to which carbon would not produce a molecule with a side chain? Addition of a methyl group to which carbon would not produce a, all of them would produce a molecule with the side chain. The addition of a methyl to which carbons would produce the same molecule, that is beta and gamma, all additions. How many valence electrons are present in these molecules? Carbon has 4 valence electrons here. 2, 1, 2, 3, 4, 5, 8. Here 5 carbons are present and each carbon has 2 bonds. So it has 2 valence electrons. 5 into 2, 10. That is 10. What is the maximum number of propyl groups that can be added to carbon alpha? What is the maximum number of propyl groups? 0. We can't add propyl groups. In the electrons in a benzene molecule are not fixed on one atom. They are valence electrons. An acidic flavor compound has been discovered. It is naturally discovered in an organic solvent, that is, it is non-polar. It does not have any natural odor or color. In the lab, you are presented with 5 vials that may contain the flavor compound. How will you attempt to detect its presence? Titrate with using this. Okay, 13 points out of 25. Use this diagram. Okay, here are 6, 1, 2, 3, 4, 5. Two cyclopropyl, 3 ethyl, 2,4,4 trimethyl hexane. Okay. 2 cyclopropyl, 3 ethyl. 2,4,4 trimethyl group hexene. The addition of a methyl group onto which carbon would change dash only to the name of the friend, that is delta. How many valence electrons are present in butane, that is 26. Okay. Which element has the same number of electrons as butane has valence electrons? Chromium, iron, that is iron. Which of the functional group is okay? No. There are oxygen atoms, but they are not bonding to any hydrogen atoms. Which molecule will have the highest boiling point? That is COOH. How many hydrogens does correct? These. Which molecule have London dispersion forces? All of them. See, why can they mix with water? They can participate in hydrogen bonding. Water is also able to do so, like stiff dissolves like. Where would you expect this? The electrons in benzene are not fixed in one atom, they are dash electrons. They are delocalized. An acidic flavor compound has been discovered. It is naturally discovered in an organic solvent. That is, it is non-polar. It does not have any natural order of valence. Take a 5-minute break. Now let's start self-study session. First, let's study about IUPAC name. Minus AI. Use this tool to either convert on to IUPAC or construct. Okay. Methane. IUPAC naming and formula. IUPAC name. In order to give compounds a name, certain rules must be followed. Okay, there are some rules to name an organic compound. By naming, IUPAC nomenclature is used. This is to give consistency to the names. A general rule is to start at the end, work backwards from left to right in the name. Okay, first we will recognize the functional group in the compound and determine its suffix. Alkane, alkene, alkyne. Okay, if a single bond is present, then its suffix is "-ine". If double bond is present, "-ine". If triple is present, then "-ine". Alcohol, if OH group is present, aldehyde, Al. Ketone on carboxylic acid. If carboxylic acid is present, OH group, oic acid ester, OH. Second, find the longest continuous carbon chain that contains the functional group. It won't always be a straight chain, and count the number of carbon atoms in this chain. This number will determine the prefix of the compound's name. Just like one carbon atom means meth, 2 carbon atoms present in the chain, we will name it at 8th, 3rd propane, 4 butane, 5th 5 carbon atoms present, then pent, 6 hex, 7 hept, 8 oct, 9 non, and 10 dec. Then third number the carbons in the longest carbon chain. If the molecule is not an alkane, that is it has a functional group, you need to start numbering so that the functional group is on the carbon with the lowest possible number. Start with the carbon at the end closest to the functional group. Okay, if some functional group will present, then we will first prefer the numbering to the carbon with that functional group or closest to that carbon. Look for any branched chain. Name them by counting the number of carbon atoms in the branched group. Note the positioning of the group on the main carbon chain. If there is more than one of the same type of branched group, then both numbers must be listed, like 2 and 4. Okay, one of the prefixes listed in this must be used, like if 2 branches are present, then we will use prefix as dry. If 3 chains are present, we will use tri. If 4, then we will use tetra. To name them, take the name of the halogen atom. For example, iodine, replace the ion with O. Fluoro, chloro, bromo, iodo. Okay, give the halogen atom to a number to show its position on the carbon chain. If there is more than one halogen atom, the number should be listed and a prefix should be added. The halogen atoms must be listed before the name of the main chain in alphabetical order. Combine the elements of the name into a single word in the following order: branched groups, halogen atoms in alphabetical order, prefix of main chain, name ending according to the functional group and its position on the longest carbon chain. Let's interact with this. There are text 5 carbon atoms in the longest carbon chain for an organic group. What is the prefix? Is pent. Yes. The di in propane 1,2-diol tells us that there are dash branched groups or functional groups. There are 2. What is the correct suffix for an aldehyde? Ol. Aldehyde is Al. Okay. The di in oct 1,6-diene tells us as there are dash branch groups of, that is 2. There are text 2 hydroxyl alcohol substituents in a compound. When we add this to the name of the compound, we will write dihydroxyl. Di in 2,3-dimethylbutane 1-ol. There are 2. Naming hydrocarbons. Naming alkanes is suffix is alkane 1, 2, 3, 4. So butane, and then butane. Name the alkanes 1, 2, 3 or 1, 2, 3. Both are same. So ane is the suffix 1, 2, 3. Two. And so at second carbon there is a methyl group 2-methyl propane. 2-methyl propane. IUPAC name for the following: CH3, CH3, CH. One, two, three, four. 1, 2, 3, 4. So we will write 2, 3. It means at second and third carbon there is a methyl group is attached. So 2, 3 dimethyl butane. 2, 3 dimethyl butane. Okay, I will understood this. Now I am clear about this naming. Let's proceed to alkenes. Okay, if there is a double bond, we will use alkene. name of this. Main chain is this, that is 1,3-diene. Okay, then at second carbon there is a ethyl group, 2-ethyl but 1,3-diene. Good. Then ine, if third 3 triple bond is present, IUPAC name of this, 1 2 3 4 5 6 7. 1 2 3 4 5 1 7. Hept 1 7 ine, diene 1 5 diene. Building hydrocarbons. Okay, now going to the second question, physical characteristics of organic functional groups. Let's visit this. Alkanes and nomenclatures. All about functional groups. Functional groups are specific groupings of atoms within molecules that have their own characteristic properties regardless of the other atoms present in a molecule. Common examples of functional groups are alcohols, alkenes, alkynes, amines, carboxylic acids, aldehydes, ketones, esters, and ethers, among others. In a typical sophomore organic chemistry course, there are about 15 key functional groups with another group of 10 so that make appearance. Okay, let's first functional group. A functional group is what we call specific groupings of certain atoms within molecules that have their own characteristic properties. Here are some of the most commonly encountered functional groups. Note that R is a placeholder for a generic carbon substituent. Alkane. Then alkene if double bond is present, alkene if triple alkyne. This is a benzene ring. Amino group, alcohol group OH, ether group, alkyl aldehyde, thiol, aldehyde ketone ester, carboxylic acid amide. The second group of slightly less commonly encountered functional groups are here. This is by means by no means it's a good start. Alcohols, ethers, amines, alkyl aldehyde. We have already studied this in previous website. Let's move to another point. Next question, physical characteristics. Intermolecular force types. Let's study about this. Intermolecular forces. Intermolecular forces. The properties of liquids are intermediate between those of gases and solids. Intermolecular forces, covalent bonds that hold atoms together in molecules and polyatomic ions. Intermolecular forces hold molecules together in a liquid or solid. Intermolecular forces are generally much weaker than covalent bonds. It requires 9 to 7 kilojoule to overcome the intermolecular forces and break both oxygen hydrogen bonds in 1 mole of water, but it takes only about 41 kilojoule to overcome the intermolecular attractions and convert 1 mole of liquid water to water vapor at 100 degrees Celsius. Given the large difference in this intermolecules determine this dipole-dipole interactions. Polar covalent bonds behave as if bonded atoms have localized fractional charges that are equal but opposite. Okay, means charges are equal but opposite, then they have a dipole in dipole bond types or dipole interaction. They have opposite charges, that is, this is negative and this is positive, then a dipole bond occurs between them. If the structure of a molecule is such that the individual bond dipoles do not cancel one another, then the molecule has a net dipole moment. Molecules with net dipole moments tend to align themselves so that the positive end of one dipole is near the negative end of another and vice versa. These arrangements are more stable than arrangements in which two positive or two negative ends are adjacent. Okay. Hence dipole-dipole interactions in above diagram are attractive, whereas in D part, okay, in this part, that is repulsive. However, attractive interactions dominate, means the dipole bond between opposite charges atoms is more dominant than others. Because each and only possess only a fraction of the charge of an electron, dipole-dipole interactions are substantially weaker than the interactions between two ions. Within a series, okay, let's study this. Doubling the distance decreases the attractive energy by 1/2. In contrast, the energy of the interaction of two dipoles is proportional to 1 upon r the cube. So doubling the distance between the dipoles decreases the strength of the interactions by 8-fold. If we double the distance, it decreases the strength of the interaction. Thus, a substance such as HCl, which is partially held together by dipole-dipole interaction, is a gas at room temperature and 1 atmosphere pressure. Conversely, NaCl, which is held together by interionic interaction, is a high melting point solid. So cyclopropane has less boiling point than dimethyl ether. Arrange this in order of increasing boiling points. Strategy for guessing the boiling points of the molecules. Compare the molar masses and the polarities of the compounds. Compounds with higher molar masses and that are polar will have the highest boiling points. The three compounds have essentially the same molar mass, so we must look at differences in polarity to predict the strength of the intermolecular dipole-dipole interactions and thus the boiling points of the compounds. The first compound, 2-methylpropane, contains only CH bonds, which are not very polar because C and H have similar electronegatives. It should have a very small dipole moment and a very low boiling point. Okay. Ethyl methyl ether has a structure similar to H2O. It contains two polar bonds CO, single bonds oriented at about a 109-degree angle to each other, in addition to relatively non-polar CH bonds. As a result, the CO bond dipoles partially reinforce one another and generate a significant dipole moment that should give a moderately high boiling point. Acetone contains a polar C double bond O oriented at about 120 degree to two methyl groups with non-polar CH bonds. The CO bond dipole therefore corresponds to the molecular dipole, which should result in both a rather large dipole moment and a high boiling point. So 2-methylpropane has less boiling point than ethyl methyl ether, which is also has less boiling point than acetone. London dispersion forces. Okay. Thus far we have considered only interactions between polar molecules. Other factors we must be considered to explain why Many non-polar molecules such as bromine, benzene, and hexane are liquids at room temperatures. Why others such as iodine and naphthalene are solids? Even the noble gases can be liquefied or solidified at low temperatures, high pressure, or both. What kind of attractive forces can exist between non-polar molecules or atoms? This can be answered by Fritz London, a German physicist who later worked in US. London proposed the temporary fluctuations in the electron distributions within atoms and non-polar molecules could result in the formation of short-lived instantaneous dipole moments which produce attractive forces. Between otherwise non-polar substances. Consider a pair of adjacent helium atoms. On average, the two electrons in each helium atom are uniformly distributed around the nucleus. Okay, because the electrons are in constant motion, because helium has two electrons, so they are uniformly distributed. Because the electrons are in constant motion, however, their distribution in one atom is likely to be asymmetrical at any given instant, resulting in an instantaneous dipole moment. The instantaneous dipole moment of one atom can interact with the electrons in an adjacent atom, pulling them forward the positive end of the instantaneous dipole or repelling them from the negative end. The net effect is that the first atom causes the temporary formation of a dipole called an induced dipole in the second. Let's move to next question. London dispersion forces weird cases. Okay, London dispersion forces get stronger with increasing molecular size. London dispersion forces are responsible for the general trend toward higher boiling points with increased molecular mass and greater surface area. All molecules, whether polar or non-polar, are attracted to one another by London dispersion forces in addition to any other attractive forces that may be present. Okay, hydrogen bonding. Molecules with hydrogen atoms bonded to electronegative atoms such as oxygen, nitrogen, and fluorine tend to exhibit unusually strong intermolecular interactions. These result in much higher boiling points than are observed for substances in which London dispersion forces dominate. Okay, if hydrogen bonding is present in a compound, then it has more boiling point than the substances having London dispersion forces more dominating. Methane and its heavier congeners in group 14 form a series whose boiling points increase smoothly with increasing molar mass. Why do strong intermolecular produces such enormously high boiling points and another usually unusual properties? Because of the polar nature of the bonds between hydrogen and electronegative elements. So strong molecular forces produce high boiling points. The large difference in electronegativity results in a large partial positive charge on hydrogen and a correspondingly large partial negative charge on the other atom. Consequently, all these hydrogen bonding have large bond dipoles that they can interact strongly with one another. Because the hydrogen atom is so small, these dipoles can also approach one another more closely than most other dipoles. The combination of large bond dipoles and short dipole-dipole distances results in very strong dipole-dipole interactions called hydrogen bonds. Okay, hydrogen bond is indicated by a dotted line between hydrogen atom and to another atom. Each water molecule has two carbon hydrogen atoms and two lone pairs. Okay, a tetrahedral arrangement maximizes the number of hydrogen bonds that can be formed. In the structure of ice, each oxygen atom is surrounded by a distorted tetrahedron of hydrogen atom that form bridges to the bridging hydrogen atoms are not equidistant. Instead, each hydrogen atom is this from one oxygen. Okay, cage-like structure of ice means that the solid is actually slightly less dense than the liquid, which means why ice floats on water rather than sinks. Each water molecule accepts two hydrogen atoms from two other water molecules and donates two hydrogen atoms to form hydrogen bonds with two more water molecules, producing an open cage-like structure. The structure of liquid water is very similar, but in the liquid the hydrogen bonds are continually broken and formed because of rapid molecular motion. Hydrogen bond formation requires both a hydrogen bond donor and a hydrogen bond acceptor. Because ice is less dense than liquid water, rivers, lakes, and oceans freeze from the top down. In fact, the ice forms a protective surface layer that insulates the rest of the water, allowing fish and other organisms to survive in the lower levels of a frozen lake or sea. What is the next question? London dispersion forces, weird case. Then dispersion forces, weird cases. Minus CI. London dispersion force is the weakest intermolecular force. It is a temporary attractive force that results when the electrons in two adjacent atoms occupy positions that make the atoms form temporary dipoles. The force is sometimes called an induced dipole attraction. London forces are the attractive forces that cause non-polar substances to condense to liquids and to freeze into solids when the temperature is lowered sufficiently. Because of the constant motion of the electrons, an atom or molecule can develop a temporary dipole when its electrons are distributed unsymmetrically. Molecular size dispersion forces are present between all molecules, whether they are polar or non-polar. Larger and heavier atoms and molecules exhibit stronger dispersion forces than smaller. Okay, if an atom has more carbon atoms, it has stronger dispersion forces than a compound having less carbon atoms. Okay, in large atom, valence electrons are more, so they are held less tightly by the nucleus. That is called polarizability. London dispersion forces tend to be strong between molecules that are easily polarized, weaker between molecules that are not easily polarized. London dispersion forces occur between all molecules. These very weak attractions occur because of the random motion of electrons on atoms. Okay, London dispersion forces is the weakest force, then dipole, then hydrogen bonding, then ion force. Types of bonds: ionic bonds. Ionic bonds are formed by the formation of cation and anion. For example, NaCl is an ionic compound in which Na positive and Cl negative combine to form an ionic compound. Covalent bonds are formed by equal sharing of electrons between bonded atoms. Covalent bonds are usually formed between two non-metals. They can be polar or non-polar. Coordination bonds. London dispersion forces example: the unequal distribution of electrons about the nucleus in an atom can induce some dipole in the atom. When another atom or molecule comes in contact with this induced dipole, it can be distorted. Let's study about the next question. What are the valence? What are valence electrons of an atom? Let's study about valence electrons of an atom minus Ai. Let's study about the valence electrons. What are the valence electrons? Valence electrons are the electrons in the outer energy level of an atom that can participate in interactions with other atoms. Okay. Valence electrons are the electrons which can participate with other atom for interactions. Valence electrons are generally the electrons that are farthest from the nucleus. As a result, they may be attracted as much or more by the nucleus of another atom than they are by their own nucleus. We have electron dot diagrams. Valence electrons. Number of valence. First column is 1, second 2, and so on. This table salt pictured in the figure below contains two elements that are so-reactive. They are rarely found alone in nature. They undergo chemical reactions with other elements and compounds. Table salt is the compound name. It forms when an atom of sodium gives up an electron and an atom of chlorine accepts it. When this happens, sodium becomes a positively charged ion and chlorine becomes a negatively charged ion. The two ions are attracted to each other and join matrix of interlocking sodium and forming a crystal of salt. This pink valence electron of Na sodium gets shifted to Cl. It becomes deficient in electron and it becomes it has excess of one electron, so both of them becomes combined with each other. Next, what is titration? Let's study about titration. Now let's practice these questions. A molecule with 5 carbons must always be called pentane. In regards to naming, the numbers assigned to each carbon atom in an organic molecule must be the dash possible. Less must be the lower possible, must be the small possible. The smallest number should be given to the functional group or any group attached to the main parent chain of the carbon. What is the formula for the number of hydrogens in an alkane? Alkane has single bond, so 2 carbon atoms are joined with a single bond and they have 3 vacant valence electrons. 3 plus 3 is 6. 2 esters and carboxylic acids can thought of opposites in what regards structure. One contain 2 oxygens and the other only one. Size, carboxylic acids are always larger than esters. Reactivity, carboxylic acids are inert while esters combust in contact with their odor or taste. Usefulness, can be thought of opposites in what regard? It can be possible. Esters, no. Size, reactivity, LDFs can be stronger. Okay, London is stronger than hydrogen bonds when the molecule with only London dispersion forces is sufficiently dash than the molecule with small, because if it has larger size, its London dispersion forces are weak or maybe polar. All molecules containing carbon are organic molecules. True. A carbon can make a maximum of dash bonds and theoretically a minimum of dash bonds. Maximum of 4 bonds and a minimum of 4 bonds. Theoretically minimums of 2 bonds. The presence of an alkene can be tested by adding bromine. The presence of an acid can be tested for by first adding a base. Despite ethanol being smaller than butane, it has a higher boiling point due to its ability to participate in the smaller size. And it also has small number of hydrogen carbons. Four out of 10. Okay. in the presence of an alkane. Testing base. Despite ethanol being smaller than it has a higher boiling point due to its ability to participate in hydrogen bonding. Okay. Now let's take a 10-minute break. You have 20 minutes to complete this test, do not rush. Now let's solve post test. Now use this diagram to answer the following 7 questions. There are dash atoms present, carbon atoms in the parent chain. Now first count the number 1, 2, 3, 4, 5, 6, 7, 8, or 1, 2, 3, 5, 6, 7, 8. Eight, 9 or 10. 1, 2, 3, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Numbering will begin at alpha. Use this information along with the previous diagram to answer the following 5 questions. Consider possible branches at carbons X, Y, and Z. X, Y, and Z. The branch at carbon Y is R called Y. The branch is at carbon Y. Methyl, methyl, methyl. Which carbon atoms can only make one more bond? X and Y, Y and Z. All of them. Y and Z. Which carbon atom is able to make 2 more bonds? X. What is the IUPAC name of this molecule? 1, 2, 3, 4, 5, 6, 7, 8, 9. Or 1, 2, 4, 5, 7, 8, 9. Starts from 7. Okay. 1, 2, 3, 4. 4, 5, 6, 8, 9. 1, 2, 3, 4. 4 methyl. 4 methyl. 5 trimethyl. 1, 2, 3, 4, 5, 6. Okay. The addition of a methyl group onto carbon dash and dash would add an extra side chain alpha beta or alpha gamma, alpha and gamma, no, gamma and delta. Delta and Z. delta enzyme. Which of the following molecules is not an organic molecule? Carbon dioxide. How many valence electrons are present in methane? 8. Which element has the same number of electrons as the methane has valence electrons? Carbon. Oxygen. Which of the following function group is most likely to taste sour? This is carboxylic acid. Can you answer to the previous question? Participate in hydrogen bonding. Why or why not? It has oxygen. It has hydrogen. Oxygen hydrogen bond. Which molecule will have the lowest boiling point? How many hydrogen atoms does an alkane with n carbon atoms have? 2n plus 2. Use the information to answer the which molecules can partake in dipole-dipole interactions? Assume each substance because all have oxygen hydrogen bonding. Assume each substance is a liquid at room temperature. Which of these molecules can mix with tetrafluoromethane? Why can they mix with CF4? It has London dispersion forces. Despite that, methanoic acid has much fewer carbon atoms than methyl cyclopentane. Its boiling point is much higher. Why? Methanoic acid. Methanoic acid has oxygen atoms. Oxygen atoms increase boiling point. Where would you expect propanol to place in this list? Between diethyl ether and methyl cyclopentane, between methyl cyclopentane and methanoic acid, between methanoic acid and decanoic acid, below decanoic acid. That is, we have to place propanol. Between methanoic and decanoic acid. Use this diagram to answer the following 4 questions. The addition of a methyl group to which carbon would not produce a molecule with a side chain? All of them would produce a molecule with a side chain. The addition of a methyl to which carbons would produce the same molecule? Alpha and gamma. Or all of the molecules will produce same molecule. How many valence electrons are present in this molecule? 3 carbons. Here 1 carbon atom is present and it has 3 valence electrons. Here 2, 5, 6, 7, 8, 9, 10, 11. 11 plus 3, 14. What is the maximum number of propyl groups that can be added to the carbon alpha? It has 2 bonds. It can accumulate only 2 methyl groups, not propyl groups. The electrons in a benzene molecule are not fixed on any one atom. They are localized. A neutral dye has been discovered. It is polar. It does not have any natural odor or color without the presence of another chemical. In the lab, you are presented with 5 vials that may contain the compound. How will you attempt to detect its presence? A neutral dye has been discovered. It is polar. It does not have any natural odor or color without the presence of another chemical. In the lab, you are presented with 5 vials that may contain the compound. How will you attempt to detect its presence? Add orange dye. Artificial orange dye will absorb into the compound. Add water. A polar compound will readily dissolve in water. Titrate it with NaOH. Will neutralize the compound. Now I have submitted my responses. Let's 16 out of 25. Four methyl, 5 propyl. Okay, this is 5 propyl, not trimethyl. Nonene. How many valence electrons are present in methane? Good. Yes, there is a hydrogen bonded to an oxygen. It has only London dispersion forces like dissolves like, so CF4 has only those. Methanol can participate in hydrogen bonding. Okay. Use this diagram. 2 out of 4. Valence electrons 38. How? 1, 2, 4, 5, 6. 6 into 4, 24. Okay. How it comes 38? Here are 6, 1, 2, 3, 4, 5, 6, 6 carbon atoms. Each has 4 valence electrons. 6, 4, 22. And again it get attached with hydrogen. 3 hydrogens. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 plus 24, 38. Okay. What is the maximum number of that can be added to carbon alpha? Propyl groups, that is 2. Why? Delocalized, not localized. Please complete both of the following survey. We didn't use Gemini or ChatGPT. How mentally demanding was this task? Good. How physically demanding? Is good. Not very. How hurried or rushed was the pace of this task? Normal. That is normal. Not. How successful were you in accomplishing your task? Perfect. How hard did you have to work to accomplish what you did? High efforts. How discouraged, irritated, stressed, or annoyed were you? Little bit. Submit. Thank you.